introduction about ultrasound from a physics point of view. And then in the second part, we will have our, at least the promised group work on MRI, group work exercise, and the second class will have the midterm. Is everybody taking the second term?
No.
Yeah?
No.
Okay, all right. So, anyways, so let me just very quickly try to give you a brief introduction of what ultrasound as a modality is. And then we'll see how, at least how far can we go with this. So first of all, ultrasound. What does that mean to you? Yeah.
Above sound,
Above, beyond. Okay, what is ultrasound? Somebody?
It's ultra.
Guys. Okay.
High frequency?
Yeah.
High frequency sound waves?
That's it. Excellent. All the answers that I heard are correct. So ultrasound, it means simply sound waves that have very high frequency. Okay? So sound waves that have that's my width, high frequency. So high frequency. How high? How high? Beyond 20 kilohertz. Okay. So if you divide, because remember in electromagnetic waves, we had something called the electromagnetic spectrum. Remember that?
Yeah.
Okay. Similarly, in acoustics, we have something called the acoustic spectrum. And the acoustic spectrum looks something like this. And so if I divide it, it has 3 regions. Okay. So it has 1, 2, and 3, third region. The lower part, so this is the frequency here. This is low frequency, and this is high frequency. High F, low F. Okay? In the low frequency region or region, it's called infrasound. Okay? And in the intermediate range, it's called the audible sound. It's the sound that we hear. Okay? It's a sound that our ears can analyze. Okay? And then we have the high frequency range or region is called the ultrasound. Okay, so this is the acoustic spectrum. What are the limits? The limits are this one. So from 20 hertz all the way to 20 kilohertz. Okay? These are my limits. So below 20 hertz is called infrasound. Between 20 and 20 kilohertz is called audible sound. This is the sound we hear. Okay? And beyond, above 20 kilohertz is called ultrasound. And this is what we use for our ultrasonic imaging as a modality. Okay? So that's what ultrasound is. So whenever you define, and I think, but one of you earlier said that, the definition of ultrasonic waves, nothing more than it's sound waves at high frequency. Okay? So now we wanted to define what sound waves are. Okay. Can somebody define for me what a sound wave is? There is a magic word that whenever you talk about, actually they're equivalent, magic words that whenever you talk about sound waves, you have to mention them.
Sound vibration.
Needs a medium to travel through, which means that they are called mechanical waves. Okay? So sound waves are mechanical waves, and other people call them, or usually they are called pressure waves. Okay? Either mechanical waves or pressure waves, it's equivalent, whether you say this or that. What does this mean? That means the wave propagates or travels through simply using pressure. It's pressure. So even when you speak, you and I, when we speak, if you put your hand in front of your mouth, you feel that you are exerting pressure on the molecules, the air molecules, and you're vibrating them, and that vibration is at some frequency, and that propagates throughout the space around you, for example, this room, and that's how everybody hears me. So you actually, when your ear detects these pressure waves that as I'm speaking, then your ear analyzes that, and that's how you hear me. So that's what pressure waves or sound waves are, nothing more than pressure waves or mechanical waves. Mechanical in the sense that they need a medium to travel through. And if you remember, and whenever you go for an ultrasonic scan, the first thing they put gel on the tissue, right on the mom's tummy.
Yeah.
The reason they do that because they want to make sure that they have a medium, a good medium that the waves travel through or propagate through to the sub regions. Okay, so that's sort of a brief intro. So how is that different from electromagnetic waves? How is this different, what I'm saying, how is this different than electromagnetic waves?
These are sound
They don't need a medium to travel. They can't travel through vacuum. In fact, they call them transverse waves. Okay? The ultrasonic waves, they call them longitudinal waves, and electromagnetic waves, they're called transverse waves. So let me run the first thing that I wanted to do. I'm going to come back to the definition of a wave in a few minutes. And that's what I want to make sure that you guys understand. But before that, I just want to show you the definition of a wave. And then I'm going to show you some of the typical waves that we see in our daily or encounter in our daily life. Okay. So what is a wave? What is the definition of a wave? The physics or the scientific definition of a wave? Somebody, you have it on the board, but I just want to make sure that you understand it. A wave, as you can see there, is a traveling disturbance that transports energy from one place to another. And matter is not transported. So you just transport energy through matter, but the molecules are still there. They vibrate a little bit, and then they go back to their equilibrium. It's exactly like as I said when you speak. When you speak, you vibrate the molecules, but the air molecules stay where they are. They vibrated, the wave propagates through. So it's just, I usually joke about this and say this is simply like an energy truck. So a truck carrying energy and depositing energy as it goes. Okay. So that's what the wave is doing. It's just simply, as the definition, simply a disturbance in the matter that just transports energy but not matter. The examples of it, of course, we have sound waves, we have stadium waves, we have water waves, we have light waves, so many of them. In fact, I have a nice example. So a sound wave, we're very familiar with it, those of you who like sports and go to a stadium. Then you see, you know what that means, but the second part, or the second picture, which shows you what a pressure wave looks like. And I'm going to come back to this, because this is what matters to us. What I want to point out here is that, remember the idea of exerting pressure? Right? It's exactly this. So I'm exerting pressure, and then that goes through the medium. But look at the particles, look at the molecules. The molecules stay where they are. Right? So they vibrate and then they are. And then we have the more, what we call the complex waves, something like water waves. So at the surface, you see that it's simply a wave, but as you go down, it's not completely a wave. There is something, as you go down. Now that does not concern us. I'm just showing you that there exists something like these type of waves. Where at the surface, you can characterize it as a noise, sinusoidal wave, but as you go deeper into the material, that falls apart. That's not true anymore. But again, this is what concerns us. Is there? So, having known or seen what the wave looks like, now we wanted to sort of look at the two types of waves. We have the longitudinal type of waves, which the prime example of that is sound. And as you can see, the way the wave is created is by simply exerting pressure, and then that pressure transports throughout the molecule, and then you create, you can look at the bottom diagram, where it's simply a pulse that travels through. Right? So that's the first type, which is sound wave, or longitudinal wave. The second type of waves is what's so-called the transverse wave. Electromagnetic waves are transverse waves. Okay? And what happens here, that I got over, because I forgot what to mention here, in longitudinal waves, the displacement or the motion or the vibration motion or the wave motion is along the direction of the motion of the particles. So the particles, they vibrate this way, and the motion travels, so it's along the same line. And that's why they call them longitudinal. Okay? Then we have the second type, which is the transverse waves. And as you can see, the motion of the particles are perpendicular to the motion of the wave. So the wave is traveling in this axis or along this axis, and the particles are vibrating perpendicular to it. Okay? So these are the two types of waves. I said longitudinal and transverse. Can somebody define them very quickly for me? What's the difference between longitudinal and transverse waves?
The particles move with the line
Along.
the motion.
Okay.
Motion,
And?
Perpendicular.
Which they're called the transverse waves. Okay? So these are the two types of waves that we want to look at. Now, again, we have the complex water waves, but again, we're not too much concerned with that. And this is another, the definition, which I just mentioned, the difference between longitudinal and transverse waves. Now, the second thing that I want to go to, before I come back to the difference between electromagnetic waves and sound waves, I wanted to look at something called the wave parameters. What is the wave characterized by? You should know this. What is the wave characterized by? Wavelength, amplitude, frequency. Okay? So these are the three main parameters of the wave. If I wanted to describe a wave, somebody says, okay, describe a wave for me, or that specific wave, then you have to know its frequency, its amplitude, and its wavelength. And so let's just make sure that, just to remind you very quickly, the amplitude is simply the height of the wave, the maximum height of the wave, and it can be positive, it can be negative. Okay, in our definition, positive, it will be compression, and negative, it will be when it's decompressed. Okay, so when you exert pressure, when it's compressed, that's positive, and when it's relaxed or decompressed, that's negative. So that's the amplitude. And the wavelength is simply the distance between the two adjacent maximum. Okay? And of course, this is amplitude versus position. If you have amplitude versus time, then the time taken between two maxima is the period. Okay, the period is simply the time taken for the wave to repeat itself, to complete one complete cycle. Yeah, one complete cycle. That's what the time. And of course, the frequency is defined as 1 over t. Okay. So from here, I can find, okay, so I know lambda, I know f, and I know a. Okay. From here, I can find the speed of a wave, which will be lambda f. Lambda is in meter, f frequency is 1 over t, so meter per second, and that gives me the speed of the wave. That's it. These are the parameters that if somebody asks you to describe them, then you can describe the wave using these three constant parameters. Okay? So that's the first, or at least that. So I have summarized that for you here. We'll come back to this example. Let's examine these three exercises. Okay. So the first exercise, the first picture here, that shows, actually the two pictures of the two diagrams, they show two waves. Okay. What is the difference or differences, if any, between the two above waves? Can somebody identify the two, the differences between, or if there are any differences between the two waves at the top here? Come on, yeah? Say again? One of them is in time, and one of them is given in. So what is that going to give you? One of them should give you the period, and the other one should give you lambda, which is the wavelength. Okay? How about the amplitude? The same in both. Now, what can you learn from, if you have something like this, what can you calculate for this specific wave? If you have a wave that is described in the time domain this way, and another one as a function of lambda, and then I can use this to calculate the speed of the wave, because I know the frequency, and with the frequency, how can I get the frequency from this? 1 over t. What's t in this case? Can you see what's t there? 6 seconds. Okay, so in this case, the frequency is simply 1 over 6, and I need lambda. What's lambda? 6 meters. So this is 1 over 6 hertz. Remember, the frequency is measured in hertz, or 1 over second, and lambda is measured in our 6 meters. And then if I want v lambda times f, that's 6 times 1 over 6, that gives me 1 meter per second. That's the speed of that of this specific wave. Now let's see more examples. Okay, how about what are the differences between, if any, among the 3 waves? So let's take the first 2 waves. What is the difference? What are the differences between the first 2 waves? The one in the top left or right hand corner. Top left. The period is not the same, but the amplitude is the same. What can you say about these 2 waves? Guys at the back there. What can you say about these 2 waves? One of them has higher frequency, because remember, the frequency is 1 over t. Right? So which one of them has higher frequency? The one with the shorter t. Okay, that's what frequency is. Frequency is 1 over t. So as t gets shorter, frequency gets higher. So when you look at the first one on the top left corner, and you say the one with the red, it has higher frequency than the black wave. Okay. How about the second one? Second, there, the triangles and the squares. Okay, the wavelength is the same, but the amplitude is about more than half, because the amplitude of the lower one is 1, the amplitude of the top one is 2.5. Okay, so these 2 waves, what I can say about them is that they have the same wavelength, but they have different amplitudes. How about the third one? Different lambda, different wavelength, but the same amplitude. Okay? So you should be able to recognize what the wave, at least the difference between the waves are. The last thing that I wanted to discuss, because we're a little bit running out of time, is the wave equation. Yeah, it's very important because this will help us analyze the wave. Now, this is a typical example of a wave traveling through a medium. And we'll come back to this when we talk about the frequency components and all of that business that we need for imaging. So the wave equation is defined as let me just write that. So y, which is a position, as a function of a position x and t, is equal to a cosine omega, kx minus omega t. Okay. Now a we know it. What's a? Louder, guys, come on. The amplitude, okay? And k is defined as the wave number, and it's equal to 2 pi over lambda. Okay, so k is actually proportional to 1 over lambda. That's k, it's called the wave number. Okay? And omega is called the angular frequency. Omega is defined as 2 pi multiplied the frequency. Okay, just in a different unit. Okay? So just so that we know, omega is a function of f. So just you can't. Another way of saying this is that you can calculate it using the frequency. So from the previous examples, if you know what the frequency is, you can calculate omega. Okay? And similarly here, if you know what lambda is, you can calculate k. So this is called the wave number, and this is called the angular frequency. Right? And of course, this will give me the wave equation. So what is that, again, what does this give me? Remember, look here, there are 2 variables. Okay, so x and t are variables, and 1, 2, 3 are constants. Okay, what did we call these guys before? If let's say if you look at this as lambda, this we look at it as f, and this is what did we call these guys? Wave parameters. Okay, so all of a, k, and omega are called wave parameters. Wave parameters. Okay. So from here in the wave equation, you can, in your the way you imagine this, that there are 3 constants and 2 variables. Okay, 3 constants, which are the wave parameters, and 2 constants, which are vary depending on the position and the time of the part of the wave action. Now, we can also define a wave moving to the right towards positive x, as I have indicated here, and also you can define it so that it's moving in the negative direction, or so the only difference between them is that this is moving to the left, okay, the negative side, or the negative direction, and that is moving to the right, and that's indicated to the positive direction. So just this wave is moving this way in the positive side of x, which is you define, or negative side of it. Okay. Let's, I think I have an example here. Yeah. Let's take this second example here, and then we'll start for today. And that's important here. Okay, suppose that I have a wave equation, y, as a function of position and time, is defined as a 0.45 sine 8 pi t plus pi x. Yes. By the way, and I forgot to mention this, and I'm assuming this is trivial to all of you, that the wave equation is either a sine or a cosine. Why is that? Because what is a function of a sine?
No.
Yeah. It simply has a period, and it's what we call sinusoidal or cosine, which the only difference between a sine wave and a cosine wave is what? And somebody, what is the difference, the only difference between a sine wave and a cosine wave? Okay, so this is x, and this is the answer. Let's start with the cosine.
Cosine y-axis.
It starts from cosine 0 is equal to 1, and then it goes like this. Okay, and so this is cosine theta. And if I have sine wave, it starts from 0. So this is sine theta. Okay, this starts because cosine 0 is equal to, this is the angle, 0, pi over 2, pi, and so forth. So cosine 0 is equal to 1, or the amplitude A, and sine theta, sine 0 is equal to 0, and it starts from 0. Okay. So whether we use sine or cosine, you just have to be careful where it starts when, in this case, x or t is equal to 0. Okay? So let's go back to the question. The question we have. Now he's saying that a wave is described by this wave equation, where t is the time in seconds and x is the position or the displacement in meter. Find the amplitude, the frequency, the wavelength, the speed, and so forth. Now, how can I find immediately from this wave equation the amplitude, the frequency, all of these? Okay, so why don't we start by writing what the general form of the wave equation looks like. Sine, we said kx, in this case is plus omega t. Okay, that's the wave or the form that we know. Since it's positive, just so we make sure that everything is written. So omega t plus kx. Okay. So if you compare, this will give me A, the amplitude. So the answer there, the amplitude is equal to 0.45, whatever the units are. So if it is volts, volts, if it is meters, meters, if it is so forth, so forth. And if I want to find omega, okay, because remember, he wants the frequency. So from here, I see that omega is equal to 8 pi is equal to 2 pi f, right? So and then I have the frequency is equal to 4 hertz. Got it? Okay? How about lambda? He wants the wavelength. Since k is equal to pi, and k is equal to 2 pi over lambda. Okay? So if I cross multiply, this will go, lambda is equal to 2. And in this case, it's meters, right? Meters. Okay? So I got the amplitude, I got the frequency, I got the wavelength, this leads to lambda, and he wants the speed. What's the speed?
Speed with
Come on. Lambda f. So the speed is equal to lambda multiplied by f. Lambda is 2, f is 4, so it's 8 meters per second, right? 2 times 4. Okay? And what else he wants? Speed. Is the wave traveling to the left or to the right? Right? Left. Why? Because positive. Remember, if we go back to the previous slide, so if it is minus, then it's moving to the right. If it is positive, then it's moving to the left. Okay? And is the wave traveling? Then also, when x is equal to 0, draw the displacement y for a time duration of 2t. Okay, this is something that we need to look at together. So first of all, he said when x is equal to 0. So x is equal to 0, that means what? That means y is equal to 0.45 sine 8 pi t, because x is equal to 0. Okay? Right. So he wants me to draw it for a time duration of two periods. Okay? What's 2 periods? 2 periods are like this. This is one, it's a sine wave, so it starts from 0. So that's 1 period, and then this is the second period. That's the second period. So this will be 1t, that's t, and this will be 2t. What is the amplitude? 0.45. 0.45, and this one is minus 0.45. Okay? The only thing that I need to know what this point is, what this point is equal to, and what is this point equal to. Well, what's t? The period. What's the period?
8. 1 over f.
1 over f. What's f?
4.
4. So what's t? T is equal to? Yeah, seconds. Okay? So my t here, this point here is equal to 0.25 seconds. Okay, so this is time. This is time in seconds. Okay? And then I can work, of course, here it will be 2t, so that's equal to what? 0.5. And then I can work out these two numbers. Okay? So this will be, what is that? 0.125 and, sorry, 0.1, yeah, 25 and so forth. Okay? That's how you, just simply this is quarter, half of the period, and this is 3/2 of the period. And then you work with these numbers. That's it. Okay? So let's stop here for today. At least I'll give you an introduction. And then after the